All right. So just to finish up real quick, maybe talk about where we ended on the last lecture. We were finishing a problem using vectors and balancing equations of forces. And we have tension forces in two strings holding up a weight. Strings are making various angles with the ceiling. And so simply by setting up an equation that says that the sum of all the forces has to be zero, since the object is at rest, will give us a system of equations. So we didn't get a chance to write it down in the last lecture. Maybe we just write down the equations at least. The idea is that if the sum of all the forces are equal to zero, that two vectors are equal. So this vector on the left, which is written as a sum of vectors, is equal to the vector on the right, if and only if each of the coordinates are equal. Nicely enough, since the vector on the right is the zero vector, both of the coordinates are zero. So it means we simply have to rewrite this equation in terms of the components that we found for F1 and F2. So our equations are going to look something like, we have F1 plus F2 plus this J component is going to equal 0. So if we add the two vectors, F1 and F2, our X component is going to be norm of F1. I'm just going to keep sine of pi over 6 as it is. Hopefully everyone knows how to reduce that. It is a negative value, plus norm of F2. And this one, cosine of pi over 5, we do not know by hand. And then our third vector had no X component, only purely in the J component. So I know that the sum of those two vectors is going to be 0. In our J components, likewise, we will have norm of F1, cosine pi over 6, plus norm of F2, sine of pi over 5, and now minus 75J, or just minus 75, that quantity in the J component is going to equal 0. So we've got two equations, linear equations, two unknowns, norm of F1 and norm of F2. So we can solve this system of equations for the magnitude of each of the forces. And then once we know the magnitude of each of the forces, we can plug it back into the component form of the forces and maybe use a calculator for the pi over 5s and then figure out the component forms of the vectors. So today we want to get a little bit more into the geometry and operations that we can perform on vectors. We defined what vectors are and kind of gave you a loose definition of what a vector space is. Namely, that we can add vectors or subtract vectors, and we can scalar multiply. So the fact that we can scalar multiply means we can stretch vectors, compress vectors, and we can flip them in the opposite direction. And so today we want to talk about, today and next week, we're going to talk about multiplications on vectors. So today we're going to talk about the dot product. Next week, we will start on a Wednesday. So next Wednesday, we will start on cross products. And we want to be able to interpret what these dot products mean, how we can use these tools geometrically. And dot products are going to play a big role pretty much throughout the entire semester. So I believe you guys have completed the the preview assignments, and you should have a general notion of what the dot product is. So I'll go pretty quickly through the definitions, and for the sake of this, we're just going to work in three-dimensional space, in three space. So if we have two vectors A with components A1, A2, and A3, and a vector B, components B1, B2, and B3, we defined the dot product as this sum here. Excuse me. A2, B2 plus A3, B3. So we are essentially just multiplying each of the components of the respective vectors and then adding all of those products together. And on the notes and in the preview assignment, our other definition we have is that the dot product is equal to the norm of A times the norm of B times the cosine of the angle between them. So on the notes, I think that she did it in arbitrarily Rn space. So we can always extend this definition if we have four-dimensional space, five-dimensional space. The algebraic product here is exactly the same. Same thing in two-dimensional space, 2D, we just get rid of that one component. And then this is more of a geometric definition. So this is going to be our algebraic definition. And the one on the right is going to be our geometric definition. So the geometric definition, nicely enough, because it is given geometrically, it's going to hold in arbitrary dimensions, whereas the algebraic definition, we will need to extend algebraically based on the number of dimensions. And one question we may want to ask ourselves is, well, what is this cosine of theta? If we're given two vectors in two dimensions, it's fairly clear that if I just have two vectors, that we can measure the angle between them. But as soon as we have three-dimensional spaces or more, it's kind of unclear where that cosine of theta is, depending on how we're looking at it. So you can imagine that any two vectors are going to span a plane. And we'll get into planes shortly this semester. It's going to be a week or so. And within that plane, there's going to be a specific angle. So that's going to be that specific angle that we refer to between two vectors. So one thing we can kind of gather from this is just some understanding sort of geometrically based on the shapes, based on the positions of the vectors, of when the dot product is negative. Sorry, I didn't write out a full English statement here. So for which situation is the dot product between the two vectors going to be negative? The three examples we want to look at are going to look like that. They're going to look this. And then we also have an obtuse angle. So this one's a right angle, acute angle, obtuse angle. So when is the dot product going to be negative? Well, if I'm just giving arbitrary vectors in space as pictures, we want to get some intuition based on the geometric definition. So the geometric definition of the dot product says it's going to be the magnitude of A times the magnitude of B. Both of these quantities are always positive since we're computing the magnitude, the length of the vectors. Cosine, however, can potentially be negative. So when is cosine going to be negative? It's going to be negative whenever the angle between them is bigger than 90 degrees. So cosine is going to be positive in the first quadrant of our trig Cartesian coordinate system, and it's going to be negative in the second quadrant. So anytime the angle is pi over 2 to pi, it's going to be negative. So these two vectors will have a negative dot product. These two, our dot product is going to be what? It's cosine of pi. Going to be 0. And then here, since they're pointing in the same direction, the cosine of the angle, again, angle smaller than 90 degrees, here we will have a dot b bigger than 0. There's an example in the notes. I'll leave it to you guys to look it up. I guess this was actually used in an algorithm by some sort of like machine learning or matching algorithm on Netflix, where they categorize people based off of their likes or dislikes and based off of maybe a certain axes of different types of genres of whether you like it or dislike it. And based on that vector position, if the dot product of these quantities was positive, what does it mean for dot product to be positive? It means that, well, the angle between them is less than 90 degrees. In other words, the angle, or another way to think about it, I guess, is that the vectors have components pointing in the same direction. They're pointing closely enough in the same direction. So if the dot products are pointing in that same direction, then this algorithm registered that as a good value, as something that might match a person's interests. Whereas a negative direction would tell the algorithm that this shouldn't be recommended to that person. So we'll get into that more a little bit. Let's just do some basic computations. Let's work with this dot product a little bit more on the algebra, and then we'll get back to more of the geometry and end with our geometry today of how we interpret all of this. I guess it's not purely algebra, since we will be using geometric definition. Namely, now when we have any two vectors, we can actually compute the angle between two vectors. So if we are given vector A as 1, 3, 0, and vector B as 2, minus 1, 2, we want to find the angle between them. So how do we do that? We have to use both definitions in this case. So since we actually are given the vectors in component form, we can compute a dot b using our algebraic method. So we're going to have 1 times 2 plus 3 times minus 1 plus 0 times 2. And so we get 2 minus 3. So negative 1. How does that help us? Well, we know that the algebraic definition should match the geometric definition. So using the geometric definition, let's go ahead and pick out our parts. We need to find the norm of A, which is going to be square root of 1 squared plus 3 squared, 0 squared. So root 10. Norm of B, 2 squared plus minus 1 squared plus 2 squared. That's going to give us 4 plus 4 plus 1. So square root of 9 gives us 3. So putting that all together, we're going to have -1. So I'm going to have to kind of squeeze the rest of this in here. I think it'll be better to just finish up on the space of this page. We'll have this -1 is the dot product is equal to the norm of A, square root of 10, times the norm of B times cosine of theta. So what do we get? We get cosine of theta is equal to negative 1 over 3 root 10. And unfortunately, this is not a very nice angle, at least not one we can compute by hand, at least not one we should know off the unit circle. So our theta is simply going to be written as arc cosine of negative 1 over 3 root 10. Rough estimate, how big is that angle? What quadrant should that angle be in? Is it acute, right, or obtuse? So hopefully everyone remembers all their trig, that since the ratio is negative, cosine is going to be negative in our second quadrant. So it's going to be an obtuse angle. So these vectors should be pointing in sort of opposite directions, so to speak, or at least more opposite than not. Again, let me know if I flip the page too fast, if anyone's still writing. Also, let me know if I start lagging. I was having some issues lagging in one of my other classes. Sometimes, depending on how Comcast is keeping up with the demand, I'll get some lag spikes here and there. So properties of the dot product. Let's do true false here. So all of this is from the notes. We have A dot B is a vector. True or false? So this one is false. It is a scalar. So the dot product, it's an operation where it's a multiplication on an algebraic structure. So we have an algebraic structure that is a three-dimensional algebraic structure where we can add vectors, we can scalar multiply vectors. Now when we added this dot product is actually an operation that moves us to a different dimension. It gives us a scalar value. We'll learn from the cross product. The cross product is going to give a vector value. So we want to be able to interpret these dot products and cross products geometrically. We'll get to that after the end of all these properties. Let's finish up more of the algebraic properties. That A dot B is equal to B dot A. So just from the geometric and the algebraic definitions, because multiplication of real numbers commutes, meaning I can take A times B and B times A, those are the same thing, that whether I switch the A's and B's in this product isn't going to matter. So this one's going to be true. Likewise, our geometric definition, norm A times norm B, doesn't matter if I flip the order of norm B times norm A, still going to compute the same quantity. So this one's true. Careful with this one. Mary Beth threw this one as a curveball. So now that we are introducing a multiplication on our vectors, we need to know how it's going to interact with our addition operation. So we have A dot product with the vector b plus c. So it looks like a distributive law. Careful with how you're reading it, though. This one is false because of this guy here. So we should have a dot b plus a dot c. So nicely enough, multiplication and addition always have this distributive law, no matter the type of multiplication. So a dot b plus a dot c. D says a dot a is the norm of a This one is also false, but it is close. How do we modify it? A dot a from our geometric definition should be norm of a times the norm of a. Cosine of theta, well, the angle theta that a vector makes with itself is 0, and cosine of theta is just 1. So a dot a is going to give the norm of a vector squared. And the last one, we're going to introduce some new terminology. If we have two vectors that are non-zero, so we have two vectors that are non-zero and their dot product is equal to 0. So true or false here, if A and B are non-zero vectors, but their dot product is equal to 0, what does that tell us about the angle between them? It means cosine of theta has to be equal to 0. In other words, theta has to be equal to pi over 2 or 3 pi over 2, depending on how you're looking at it. So pi over 2 is a right angle, meaning they are perpendicular. So this is true. So new terminology. Two vectors are orthogonal if let's say let me squeeze in some words. So two vectors A and B are orthogonal if the dot product is 0. So we can take that as a definition. So orthogonal means perpendicular, means the angle between the two vectors is pi over 2. Any questions so far? So let's expand upon this a little bit. So if two vectors are orthogonal, we can use this dot product to compute the angle between vectors. So let's get back to the geometry a little bit and try to understand a little bit more intrinsically what is going on with this dot product. Geometrically, what does it mean? We have geometric formula, so let's break that down a little bit. We know also at least that if the dot product is equal to 0, well, that gives us a notion of orthogonality, of perpendicularness. So what about in general? What is the dot product going to give us? So if we have two vectors, a dot b, it's going to be norm of a, norm of b, cosine of theta. Let's draw a picture. And I'm trying to think of how to draw this. Let's just draw arbitrary vectors in space here. Let's say this guy's our vector A, and this one's our vector B. And then we have our cosine of theta here. So let's take a look. What I want you to look at is just this right part. What is this B cosine of theta? So I'm going to go a little bit off the notes here and just give a little bit more to you guys. Talked a little bit of notion of vector space. And throughout this semester, I'm going to be doing this maybe a little bit, talking about both vector spaces and maybe differential equations, to drop in some hints as to what's coming next in this sequence of math that you typically take. So Calc 3 really starts to get into the geometry. Then you kind of branch after this and get into differential equations and linear algebra and take a look at some of the very similar concepts that we're talking about in this class, just a little bit more in detail. So one of the big things we're going to have in differential geometry, and so differential geometry as a field, is basically Calc 3 extended. It's all the same notions that we're going to be developing in Calc 3, but a little more abstract and in arbitrary higher dimensions. It's really looking at the geometry of calculus and geometry of what are called manifolds, which are multi-dimensional objects that can potentially form things like curved spaces. And a big concept in general differential geometry, and in particular in this class and in linear algebra, is that there is no absolute reference frame. Most of calculus so far of what we've done, whenever you have moving objects in Calc 1, Calc 2, we've talked about, you've done parametric equations. You've taken a look at some basic physics problems, I'm sure, of integrating velocity to get position and whatnot. And almost all of that is done from like a fixed reference frame. But you also have to think about, well, from that reference frame, it's from an outside observer, maybe observing a rocket shooting off in space, where we model the systems of equations. So if I have one observer observing a rocket and a different observer observing that same rocket, but how they observe it is going to be different, especially if one of the observers is sitting up higher on a tower, or maybe one of the observers is sitting in a helicopter and that helicopter itself is moving, and then they're watching a rocket launch from afar. The way they measure that and the way they observe that is going to be different. So this is kind of a lead into just a baby introduction to that, of what we're going to see in Calc 3, that we got to start to play around with this idea that observing a system on a fixed reference frame maybe isn't the best way to look at the system. As I've drawn it, I kind of drew these two vectors in just a blank arbitrary space. If we wanted to add a reference frame, let's see, let's pick red. Or no, let's keep our black. And I'll just draw dotted lines. So we have our typical XY coordinate frame. This might be some fixed reference frame that we have on our system, but the given reference frame that we have isn't always the best way to look at things. And we'll see some examples here in just a moment. Maybe given two sets of vectors, we like one of the sets of vectors or one of the vectors more so than the other one, or we want to kind of keep that as this is a direction of travel. So we'll see this a lot whenever we have moving objects, or especially vehicles that we ourselves are sitting in, or we think of the vehicle as being sort of the key component of the system. So for example, a plane, a boat traveling, and then maybe on that moving object, there are different forces, different vectors being applied. So maybe we want to prefer this A vector instead. Maybe this XY coordinate isn't the best frame to look at, and we really like this A vector. And what do we want to do now? Well, relative to this A vector, we want to take a look at this B vector. We want to know information about vector B, but not necessarily in our XY coordinate frame. We want to look at B somehow relative to A. So hopefully you guys can see that at least in the direction of A, one thing we can do is do what's called an orthogonal projection. That is, again, we like the vector A. We want to use this as some basis for our framework. And well, now relative to A, I want to project and look at components of B in the direction of A. Well, we've actually got that term algebraically sitting up here. The length of this vector here is the magnitude of B. So what is this magnitude of B times the cosine of theta? That's going to give us this component right here. So geometrically, what is the dot product given? Well, we're taking the component of B in the direction of A and then scaling it by the magnitude of A. So we can think of the dot product as a scaled projection. So it projects the component of B onto A, but since it's a multiplication, we also have to take in the size of A into account. So it's like projecting B onto A and then scaling that by the length of A. So let's make a little more rigorous definitions off of that. So some questions we might want to ask then, well, is what is exactly that scalar component? Or what is the, let's call it vector component of B in the direction of A? So how would we find that? So let's redraw the picture on this page. We have our vector A, our vector B. And so what we're looking for, again, if we don't have a reference frame, or maybe a reference frame is given that may not be the best, we want to break down a vector B and know this piece here. So again, sometimes we have, or I guess our work from the previous days, we define A, let's give it just coordinates as A1, A1, A2, and B as B1, B2. So just to explain this in a slightly different way, well, what does this mean? This is our projection of A onto our X direction and our y direction. Likewise, our projection of B onto our x direction and our y direction. But that is assuming we are given a framework of x and y. All this is saying is that I can write A as a sum of two vectors. I have a vector with a magnitude in the x direction plus a vector with a magnitude in the y direction. We know that we can break down A. So just a little aside here, that if we have our framework, then we can break A down into its components on the x direction and our y direction. Maybe I'll use different colors for our x and y. But maybe instead of x and y, I want to break a vector down in terms of some components relative to a different vector, because we like that vector in terms of a direction of travel. It might be a boat traveling, and we know that that direction of boat, if you're on the boat, the direction you're traveling is straightforward. So if we want to break down vector B in terms of those components, we need a tool to do so. So we're going to call this piece here the projection onto A of vector B. So think of this projection as an operator, as a function. It is taking our vector B and projecting it onto the vector A. So how do we figure that out? Well, from our previous discussion, our dot product gives just that. The only problem is that the dot product is going to scale this projection by the magnitude of A. So what do we want? We want the unscaled projection i.e., we want to project B onto the directional vector of A. i.e., the unit vector in the direction of A. So we just have to make A a unit vector. So how do we do that? We are going to make our definition of the projection of B onto A is going to be the dot product B dot the unit vector of A. However, we're in a little bit of a problem. So I guess we're doing this a little bit out of order of how we could develop the material. Let's actually do two things here. This one's incomplete, so we'll come back to that in just a second. Let's actually define the component of B onto A. So what do I mean by the component? It's essentially the same thing, but just the size, just the length. So let's go back up here for a second. Sorry, was everyone finished writing that? This one we still got to modify. I'll come back to that. It's a quick modification. And let's just take a look at geometrically what's going on here, because I want everyone to understand this. When we have our typical vector breakdowns in our x component and our y components, when we mean the component in the x direction, we just mean the size of that vector in the x direction. Size of the vector in the j direction. So our A1 and our A2. So what is this guy down here computing? Well, B dot A divided by its norm, all it's doing then is taking the dot product of B, or the length of B, and I guess we can write this down geometrically. This is the norm of B times the cosine theta. So this is giving us that scalar component. Anytime it says component, we mean the scalar, the length, the actual value of B in the direction of A. So just the size of that piece. If we need to attach the vector direction and actually make the vector projection, so when we see this projection of B onto A, we mean the vector projection. So not only do we want to keep track of the component, the length of that, we also need to tell us what direction are we pointing in. Well, we're pointing in the direction of A. So we're going to multiply this times A over norm A. So this gives us our components. And then this is our direction. If we want to simplify that formula a little bit, commonly written as B dot A, sometimes you switch around, or you can write it as A dot B over the norm of A squared times A. So this is a scalar, and so it's just going to scale A by the appropriate quantity. So of course, still pointing in the direction of A, and then we're just scaling this A vector so that it matches this. One thing to note is that this holds whether or not the angle is positive or whether the angle is acute or obtuse. So even if the angle is bigger, if B were pointing in this direction, we would get essentially the same scalar components, except the scalar component might be negative in this case. Just like having a negative component in the x direction points in the negative x direction. A negative component of B onto A just means B is pointing in the opposite direction of A. Okay, there's one more thing we want to pick out, and let's pick a slightly different color. Let's see if we can see something. Let's use bright green. The other thing we might want is the orthogonal component. So in terms of creating a new reference frame for us, we like the XY reference frame. It's just they're perpendicular, and we can create a nice grid and scale our space based off of how many units we need to walk in the X to how many units we need to walk in the Y. That will give us a coordinate system where we can plot any points. We can plot all sorts of vectors. Well, if we want to modify that vector space, or excuse me, that coordinate frame, especially relative to a given vector, our main vector we're looking at A, we might want to figure out, well, what is the orthogonal component going to be? So we call this piece the orthogonal component of B onto A, or the orthogonal projection onto A of B. Any ideas how we would find that?
Just the orthogonal component would be the magnitude of B sine theta.
Good, that is correct. So maybe we can write it down, but it's not very handy. So basic geometry, magnitude of B sine theta. Why is it not terribly handy? Well, we first have to compute the dot products, use the dot product, do some other calculations with the magnitude to compute the angle first. Once we know the angle, well, then we could compute B sine theta to find that component. There's actually a slightly quicker formula, and let's use some tricks using our notion of angle and vector addition. I know that, so the red piece plus the green piece has to equal B. So in other words, the projection of B onto A plus the orthogonal projection has to give us back the original vector. In other words, if we wanted to just find the orthogonal components, we could take B and start with the original vector and then just subtract off the projection. Another term we call this projection is the parallel component. So if I take B and subtract off the parallel components, we're left with the orthogonal component. And I'll leave it to you guys to check, see if that should compute B sine theta. Any questions? So we're about out of time for today. I'll go ahead and leave the examples to you guys. There's a couple examples in the book, one involving work. Let's maybe just write that down real quick. It'll come up a lot this semester. If I have a block and I'm dragging this block along the ground, but I'm pulling because I'm too tall, and we're pulling this guy at some angle, theta. Well, the direction of our force is going upward. However, we're not lifting or we're not pulling enough to really lift this block up. The direction the block is traveling is still just going to be going horizontal. So our work is the force dot product with the displacement vector, or the direction of travel. And so hopefully you can kind of see where this comes from. I think hopefully you guys have all had basic physics in high school where work is force times distance, but now we have multiple dimensions. And so the only work that's going to be done, the only amount of energy that we really need to expend is the work or the force that's applied in the direction of travel times the direction of travel. And so this is where we get our dot product. Essentially, we're projecting the force onto the direction of travel, but then we also need to scale it by the length of travel. And so we immediately return that dot product in that notation. So take a look at that. Take a look at the other example. It talks about the speed. It's kind of like a plane is traveling, and then there's a direction of a wind. And we want to maybe break down this direction of wind and see how much of the component of the wind is pointing with us is going to give us a tailwind, and then how much of the wind is going to give us a crosswind. So another example like that in the notes. Take a look. There might be an example or a question like that on the homework as well. And I'm happy to go over any of that during office hours, or maybe beginning next lecture if you guys need it.